Welcome to the Explainer. Today, we're diving into a really cool paper that tackles a huge question. How do you make AI more powerful without, everything just blowing up? Let's dig in.
All right, so let's start with that big question right there. You see, as we build these massive, more and more complex AI models, we keep hitting this wall, right? This trade-off between making them smarter and making sure they don't become dangerously unstable. And that's the story we're telling today. A really promising idea, a hidden, almost catastrophic flaw, and a seriously brilliant solution.
So to really get why the solution is so cool, you got to understand the problem first. And it all goes back to a foundational piece of modern AI architecture.
Okay, so for years, this thing called a residual connection has been the absolute bedrock of stable AI. You can think of it like a perfectly engineered information superhighway. It lets data just flow smoothly through all the different layers of the network, making sure nothing gets lost or scrambled along the way. It's the secret to keeping these deep networks stable.
So naturally, researchers thought, hey, what if we make this highway even better? And that led to this new idea called hyperconnections, or HC for short. The logic was super simple and honestly, pretty exciting. What if we just add a bunch more lanes to our information highway? I mean, more lanes, more traffic, more power, right?
Well, here's where it gets messy. And it's a big catch. The paper puts it perfectly. Yeah, they got a huge performance boost, but adding all those extra lanes fundamentally broke the rules that made the original highway work so well. It was basically like adding a dozen new lanes to a freeway, but ripping out all the traffic signs, the lane markings, and the speed limits. The result? Total chaos.
So what does that kind of chaos actually look like inside an AI model? Well, it's something called uncontrolled signal amplification. The information flying down these new lanes just starts, exploding. It bounces around, gets stronger and stronger, and creates this massive, out-of-control pileup, a total traffic jam.
And look, the scale of this problem is just wow. We are not talking about a little rounding error here. The signals were blowing up to nearly 3,000 times their original strength. 3,000x. That just completely torpedoes the entire training process. The model becomes literally untrainable. So, how in the world do you fix a 3,000x signal explosion? Well, you don't fight fire with more fire. The answer was to restore order with a really elegant mathematical set of guardrails. Let's see how they pulled it off.
And this brings us to the core breakthrough of the paper. Manifold-Constrained Hyper-Connections. We'll call it mHC. The idea is just so brilliant because it's simple. You keep the awesome, high-capacity, multi-lane highway, but you install this incredibly smart mathematical traffic management system to make sure everything stays in its lane.
And this slide just lays it out perfectly. The old way, the unconstrained HFHC, was a total free-for-all. Signals could just amplify themselves into oblivion, leading to that instability we talked about. But the new way, SEM-HFHC, forces those connections onto a special mathematical structure, a manifold, that acts like a strict set of rules. It guarantees the signals stay stable and controlled. Okay, so mathematical guardrails sounds great, but how does it actually work? Well, it's not magic, but it's pretty darn close. It all comes down to the really cool properties of a specific kind of matrix.
The secret sauce here is something called a doubly stochastic matrix. Now, I know that sounds super complicated, but the core idea is actually pretty intuitive. Imagine it's a grid of numbers, where every single row and every single column adds up to exactly 1. What that does is it forces the information to be perfectly balanced. It ensures no signal gets lost and no signal gets overamplified. Everything that goes in comes out, perfectly distributed across all those lanes. And this special structure, this matrix, gives you 3 incredible guarantees. First, it preserves the strength of the signal. It's like a governor on an engine that just stops it from redlining and exploding. Second, that stability holds up layer after layer after layer. You can stack hundreds of them and it stays stable. And third, it makes sure all the information from the different lanes gets mixed together smoothly and robustly. It's not just a patch, it's a complete fix.
Okay, the theory is really elegant, for sure, but the million-dollar question is, does it actually work in the real world? Let's look at the results.
And the results are just night and day. On the left, you've got the original HAC model going completely haywire, with that signal gain skyrocketing to almost 3,000. Now look at the right. That's our mHC model. The signal gain is totally under control, staying below 1.6. That's not just a little better, it's a reduction of 3 orders of magnitude. The chaos is gone, tame. And you can literally see the difference with your own eyes. On the left,
That's the connection matrix for the unstable HNC model. It's all over the place, right? Wild, erratic, spiky. Now look at the one on the right for mHC. It's orderly, it's stable, structured. It's exactly what you want to see. The mathematical guardrails are clearly working.
So, stability is great, but does it actually make the model smarter? The answer is a resounding yes. Look at this table. Across all these really tough benchmarks, tasks that require genuine reasoning, not just spitting back facts, the mHC model consistently beats not just the original baseline, but the unstable HC model too.
So let's break that down. The bottom line is this. mHC isn't just a fix, it's a straight-up upgrade. We're seeing real, significant performance gains, especially in those tricky reasoning tasks. And get this, it does all of that with only a tiny 6.7% increase in training time. That's an absolutely incredible trade-off. More power, more stability for barely any extra cost.
All right, so let's zoom out for a second and think about why this really matters. Because this is bigger than just one clever trick or one specific model.
The authors themselves put it best. This isn't just about fixing a bug. It's about lighting up new pathways for how we design the next generation of massive AI models. This is about building better, more stable foundations for everything that's coming next.
And that leaves us with a really fascinating question to chew on. For the longest time, the mantra in AI has been go bigger. More data, more parameters, just more. But what if this paper is showing us something different? What if the next huge leap in AI isn't just about getting bigger, but about getting smarter, more elegant, and more stable in how we build things? That's the really exciting possibility here.